So welcome everybody. There's a few names I'm not familiar with, so I will just quickly give a little hi from AnaEE and explain who we are. So we're a European Research Infrastructure Consortium, which means we are a huge research infrastructure working within the EU, and we have a lot of facilities and experimental environmental measurements that we do across Europe and across different facilities across Europe. And I am part of the Technology Centre of the AnaEE project. And as part of the Technology Centre, we've decided to start a TechUp webinar series where we introduce industries or companies or researchers that have created some new state-of-the-art technology, and we invite them to present their new technology to the research group. And this is the AnaEE research group and beyond. So we hope that we can have as many interesting discussions as possible. So the format of this webinar is going to be a 20 to 30 minute presentation by the speakers, which is David and Russell. And following that, there'll be some questions. So feel free to speak out if you have any questions. But a little bit about David and Russell. So they're here. They've joined us from all the way in Ohio. And they are part of S4 Mobile Laboratories, who are a company that are working with terrestrial measurements of soil carbon. And they will be presenting their product, which is Subterra Green, which is a soil lab device which is used in agricultural fields to map chemicals on site and in real time. So it's a very exciting product, and I'm very excited for them to take over from me and discuss what they're about to discuss. So welcome.
Thank you for the introduction, Rachel. I am Russell Pier, the Technical Sales Manager for S4 Mobile Laboratories. However, I've got backgrounds in archaeology, and I do have backgrounds in earth and environmental sciences as well, kind of all over the place in terms of my education and experience. And then I'm also here today with Dr. David Perry. He's our CTO, and he's our spectroscopist and physical chemist. So when it comes to any technical questions, David's going to be your guy. So with that, I'll hop right into it. So at S4, several years back, we recognized the importance of determining the amount of soil organic carbon. And this is one of the key nutrients when it comes to agriculture. It is imperative for soil health, and with higher soil organic carbon, you're going to have increased crop yields. And of course, increased crop yields means farmer profits. If farmers or service providers can sequester more carbon in their soil, that can also contribute to a carbon credit market. So even more profits for farmers and better for the environment as well. So we wanted to figure out a way to take part in this and measure the soil organic carbon as precisely as we can to help forward soil health and farmer profits. The solution to this is to use soil spectroscopy, and David will get into more of this in a minute. But very briefly, soil spectroscopy is just using visible light, normal light, to determine the composition of a substance. So we're looking at soil, we're looking at soil organic carbon, bulk density, and water. Now, bulk density is not something you can detect with spectroscopy, but we can detect it with a penetrometer. So this is our Subterra Green device right here in this image, and you can see some of the labeled pieces and parts. Some of our spectrometers are load cell. That's the thing that measures insertion force of our probe. We have two spectrometers, a 400 to 1100 nanometer and an 1100 and 2500 nanometer spectrometer. We have a GPS on top of the unit as well, so we can map where data is being taken in space, which is very important for soil carbon mapping. Our probe is kind of the thing that makes the magic happen, if you will. This is proprietary, and it's an all fiber optic design, and go down to 90 centimeters into the soil. Now, typically, for soil organic carbon, it's usually around the first 30 or 40 centimeters that most folks tend to care about, but 90 just for good measure. Alrighty.
Okay, thank you, Russell. I just want to say a little bit about where we are on this. There's two research projects that are now participating in the measurement of soil organic carbon using the Subterra Green. And you see there in the upper picture at the right, the team there at Boku, Vienna. They're part of the European Union FENET project from 2023 to 27, and that's through that project we actually make the connection with AnaEE. from 2023 through 2025 now. There's been extensive studies in cropped fields in Austria, and that's where you see the picture there. And soon, within a few weeks, the instrument will travel to Portugal, and there are sites there that are selected, an ecological restoration site in eastern Portugal, and also a commercial valley and vineyard in the Douro Valley. The project that we've been involved in directly with S4 Mobile Laboratories is the sponsored by the United States Department of Agriculture, and that's what we call in the United States a small business innovative research grant, and the federal government through that department provides support to young companies such as ourselves to engage in technical research to demonstrate the technologies. It's de-risking the technologies is what they're funding, okay? We also have additional support from UPL, formerly known as United Phosphorus Limited, an international agribusiness company. The phase one of the project was in 2022, and in that we showed that we can map the soil organic carbon in 3 dimensions in certain cropped fields that we chose for modeling. There were 6 different sites across Ohio where we're located. Phase 2, which is what we're now involved in, and in fact is just finishing this month, is studying corn and soybean fields in what the United States Geographic Service calls MLRA 111. And that's the area outlined in red at the map there on the right side. That area is just about the size of Austria. Okay, so it's a very large agricultural area, important corn and soybean area in Ohio and the state of Indiana in the United States. These graphs show the spectra, examples of the spectra that we record with the Subterra to show the difference between high organic carbon soils and low organic carbon soils. If you know from your own life experience that good black soil is high in organic matter, and that darker color is what we can detect and quantify with the Subterra. We also measure spectra through the whole fiber optic region in the infrared. This is just the visible, very near infrared portion of the spectra. But you can see the green graphs there are areas of high organic carbon, and the blue graphs are areas of lower organic carbon. And you can see the difference between them is this bulge, a large absorption band extending through much of the visible region of the spectrum. And the difference is the red line at the bottom, and that's essentially the spectrum of soil organic carbon, okay? However, to do the analysis, we actually use machine learning. So the calibration and validation of this with the Subterra Green uses machine learning, and we calibrate the Subterra data against the laboratory analysis of soil cores. That is the standard, currently accepted standard for determination of soil organic carbon. The input data, that's the data that is measured with the Subterra. Okay, the spectra over the range 400 to 2500 nanometers, that's the whole fiber optic range from the visible through the near infrared. We measure depth into the soil, the force required to insert that probe, which is 13 millimeters in diameter, to push that into the ground down to 90 centimeters depth, recording spectra at each depth. And the GPS coordinates. That's all the data recorded by the Subterra. And we also include as input data pre-existing geographic data. This is things like the topography and the topographic data compressed and manipulated in certain ways that are useful for this purpose. The calibration data in the middle column of that chart there is laboratory analysis of the soil cores, and we can get soil organic carbon by dry combustion with a correction for the inorganic carbon. And in our case, this is done by a commercial company which is certified for that purpose. We measure the bulk density, that's the mass per in situ soil volume, which is needed, in fact, to get the carbon stock on a plot of land, and also the water content in the soil. And those things are all measured in the lab in a subset of the locations that are sampled. And so by the machine learning process, we calibrate the input data against the calibration data. And then once the calibration is complete, we have a model for treating the input data to generate predicted values of the output data. And the output data are those that are listed there, A, B, C, D, soil organic carbon concentration, soil organic carbon stock on a site, bulk density, and water content in the soil. We have a systematic approach for determining the best machine learning model. Okay, and there's several different stages which you can see there. Pre-processing, standardizing of variables, variable reduction, choice of the regressor and the parameters for that. I won't say more about this, but I could answer questions on that. So we do have a systematic means of finding the best model within the domain of selections that you see here. Now the data, we collected a great deal of data over this whole large agriculturally important area. 47 different sites, which were selected to be representative of the whole area. So when it's done, we have a model that we can expect to have valid data, a valid model over the whole of that large agriculturally important area. For each soil core that is taken, we divide it into 7 depth segments, so we get data as a function of depth that are calibrated. The spectroscopy, we actually measure 20 or 30 different depths into the soil, so it's a finer gradation for the spectroscopy. In total, we had about 5,000 lab analysis, 64,000 in situ spectra in this phase of the project. So there's a lot of data. Now, to get good validation, we divide the calibration data into 3 groups. 60% of the data is used as training data to train the machine learning model that we're testing. 20% of the data is used for validation data, and with those data, we select the best model out of that array of models that were represented schematically on a previous slide. And so that after that, we then have the best model. And with the best model, we then test the quality of that best model with the remaining 20% of the data, which is the test data. So the test data have never been used in any way in selecting the best model. And so that gives us a measure of how good we're doing and how good we can expect to do at other locations within the project area. This is a measure of the quality measures that we have using those test data. RMSE, root mean square error, megagrams per hectare. The R squared and the RPIQ, which is a good performance indicator. Something greater than 2.7 is considered to be a good model. There's several different levels of the tests we did using spectra only as the input data, spectra plus the depth measured that we measure with our device, and spectra plus auxiliary data, which now also include pre-existing geographic data. So one can include any data that one has on hand, particularly systematic data, into the design of the model to get better values. And you see that does improve the quality of the model in a measurable way. This is an example of the output, which can be useful to agriculturalists and researchers, as a map of the carbon stock on one of the test sites. This was actually a test site from phase 1, but we have this very nice graph here, so it gives a representative. You can see the aerial view of the farmer's field and some of the farm buildings off to the right-hand side there at a location in Ohio. And the contour plots in that diagram are the carbon stock at that location that result from the analysis in megagrams of carbon per hectare. And you can see there's considerable variation over a field, which if you just look at it looks like it's pretty uniform, but it's not uniform when you do the measurements. Okay, Russell, I'll hand it back to you.
All righty, thank you, David. So some advantages of using spectroscopy for soil carbon measurement are, well, there are quite a few of them. Traditionally, I know David touched on this a little bit, is one would go out into the field. One would have usually a team of 2, maybe 3 people, take soil cores. And, this involves a big slide hammer and a large core. We have in imperial measurements, it's about a 4-foot core. So you're getting quite deep into the soil. You have to take the soil out. You got to, throw it in a cart and send it back for some processing. So this involves, dividing the sample up into multiple pieces and then sending that off to a lab for processing and analysis. Generally, this takes quite a bit of time, and it takes a lot of effort to do. There's a lot of moving parts involved in this process as well. I know in the US here, and this does not include labor time, this is just for lab processing, it usually costs about anywhere from $10 to $20 per sample. So one advantage of using the Subterra is that we can get that cost down to about 5 cents per sample over the lifetime of the unit, which is almost, well, not infinitely cheaper, but much cheaper than doing traditional sampling. Another benefit is that it is much quicker. It usually takes about 90 or so seconds to do an insertion, depending on the parameters that you set. So it's much quicker to do compared to taking a soil core and, of course, waiting up to a couple weeks for your results back. And you get results in situ in real time out in the field if you want to use it that way. Our accuracy, I know David touched on this as well, is comparable to lab measurements, in part because we've ground truthed our results with spectroscopy to soil coring measurements. So this is already a huge piece of data, but we also get much better precision because you take so much more data when you do an insertion with the Subterra. You can track the amount of carbon that is changing in the soil over a year-to-year basis, which is something that is very, very difficult to do, if not impossible to do with traditional methods. It might take 5 or 10 years to show a difference in the soil. Farmers want to change up their practice and try to get more carbon in there. So you can get much more precision with the already established accuracy of traditional lab measurements. And again, we can map in 3 dimensions, which is immensely helpful, so farmers can figure out exactly where and even how deep in some instances to focus their efforts for soil carbon sequestration. So for a while now, I know David touched on this as well. We've been working with FENET. We've actually been working quite closely with Boku University, and they have UNIT. They've been doing some work and research with the Subterra Green for a little while now. But AnaEE, I think, can get involved as well, and there's still a lot we would like to be able to do with the Subterra. One thing that we would love to be able to do and get AnaEE's help is expanding our models. Currently, our model is only really kind of set to the Midwest here in the United States, so Ohio, Indiana. So to expand our model, we would need to take just a sample, soil core or 2 in an area of interest where one would want to use the Subterra, and then implement that into our existing models to expand its testing capability. So that would be a huge thing to be able to do for us to just grow our model. We are also interested in detecting other things in the soil beyond carbon, water, and bulk density. We've been asked about nitrogen, phosphorus, potassium, and even in some cases in the Western United States where the climate's very hot and dry, we've been asked about salinity, so salt detection of the soil, which is very important. So I think the expertise at AnaEE can really help us flesh out this technology and really get it in a spot that is useful for everyone, researchers and agriculturists alike. Currently, the Subterra Green has been available for research projects. And again, I mentioned Boku. UPL has a unit. They've been doing some work with one as well. We are really in the stage right now of refining our modeling. We've just come off of the USDA SBIR Phase 2 project, which really proved out the technology in a field setting. So it's just a matter of refining models, expanding our capabilities, and researchers are a huge part of that. In the meantime, up until the start of 2026, we aim on making a whole bunch of quality of life changes to the programming, again, expanding modeling. and really getting the tool in a place for commercial use. And we hope to do this by the start of 2026. And with that, that's all we've got for you today. I hope you enjoyed. And again, thank you again for letting us, allowing us to join and present to you all today. It's been a wonderful experience. And I think with that, I will open the floor to questions. So just feel free to jump in and let us know what you got.
Yeah, I just want to say thank you very much to you both. You did an excellent job, and thank you for being our kickstarting presenters of the series. I can see we have a hand up from Klaus, so I will let him ask away.
Yeah, thanks a lot, both of you. It was very, very interesting, and I do have a lot of questions actually. Maybe some technical first, because you said now if I understand correctly, you've been working primarily in agriculture, and maybe you don't have the big problem there with actually inserting the probe 90 centimeters into the soil. Do you ever have problems hitting rocks, and what happens then?
Okay, sometimes even in the Midwest of the United States, there can be an obstruction in the ground. If there's a small rock, even a small one the size of your thumb, or a bigger one, clearly, the probe can hit that and come to a stop.
Okay, so then you have to move it and try again.
Yeah, so if we do that, then we just move over a few centimeters and insert the probe again. And unless you're in a very rocky soil, then that works pretty well. The rockiest soil we ever encountered is with Boku and the shores of the Danube River, which river has moved its path many times over the generations, and the soil is filled with these round river rocks. And the Boku initially had trouble getting the probe in, but then in the wetter part of the year, they were still able to get the probe through down to a good depth, approximating 90 centimeters in many places, right? But that's really the hardest test that it's faced.
Yeah, but it means that it's actually constructed to stop so that you don't break it.
Yes, it has a maximum insertion force, the way we have it set up, of 300 pounds, which is I know 130, 40 kilos, something like that. But that is adjustable. It could be more or less, but that is a usable range. And what it does is it approaches that insertion force when the soil becomes very hard and meets rock. It just slows down. And sometimes when it hits a rock, if it's not hitting it square on, it can just sort of slide past and continue its path down further into the ground, depending on, ground has marvelous heterogeneity, as you know. So.
But if it goes all right, did I get you correct? It takes about 90 seconds only to do the whole.
To go into the ground recording spectra. It goes in and stops in stages. We had a movie of that happening, but we controlled that for length purposes. It just goes in steps into the ground in a programmable series of depths where it's making the measurements. And then when it reaches the bottom, it stops and comes back up. So that insertion, including the spectra, takes about 90 seconds, yes.
Okay. And right now, the projects you are interested in would be one, for instance, where we borrow a unit from you, or is it that the project buys one, and how does that?
With Boku, it was a Horizon grant, the FENET project, and that cost of the instrument was built into the proposal. Most of the cost of that project is the personnel time. It's always the big expense. That doesn't mean there couldn't be a different business model, but that's the way we've done it with them. Right?
And the business model, when you start selling on the market, is that still that the unit costs something, but then you also pay for the analysis, or how is it?
with the unit, it would come with as a commercial basis, like to an end user rather than a researcher is going to do their own calibrations, right? But it would come with a calibration model that's applicable to the user's territory, or we would work with the user to extend the existing calibration model to their territory, and that would be included in the purchase price.
Okay.
Now, as a company, you always need ongoing revenue, so further upgrades to the model and improvements, that could be part of a subscription that comes with the instrument, right?
Yeah, thanks for the great presentation. Kind of a blunt question. Why is not everyone using it?
Well, this is new, okay? The first thing you have to do is build the thing and then use it in a way, do the validation and calibration so that anybody who's a skeptic can see, yes, you've done the work carefully, it's systematically tested, the statistics, the database is there to support it. And that's just, we did this before on individual sites. This recent work we finished is now to be applicable over a large, important agricultural area. So that's the next step. Now we'd like to extend that with the help of other researchers, such as Boku, to other diverse agricultural areas, right?
Okay.
And then, as Russell said, in 2026, we hope to be able to be far enough that some journeyman users who are not researchers would use it just because they want to get the results, right?
Okay. Maybe another question. So it's interesting that I'm also part of AnaEE, Eric. So I'm a science project manager at AnaEE. And it's very interesting, like, to see your experience of, private company collaborating with EU project. And well, we are also thinking about maybe, kind of extend that effort. So I was wondering, like, how did it work for you so far, being part of the EU project from administrative and bureaucracy perspective? Maybe if you could share that.
Well, the European Union has these marvelous, consortium project. FENET is one of those, the Big Horizon project. We don't have the equivalent in the United States, okay? We've gotten the taste of paperwork from that, although we are just the little appendage hanging off the edge of Boku. And so they handle all that paperwork for us, right? So it hasn't been a problem for us, although I know that the principal institutions participating do have a lot of things they need to attend to, right? We're even though we're a company by heritage, we're academics, we do research projects, we operate with the Boku in a collaborative way. They're doing a research project. We want the project to work and produce valid data. We work with them on that if they have problems. They do, however, do their analyses under their own scheme. They have their own expertise, which may be greater than ours, in fact, for how one should do machine learning algorithms, what kind of data to be included. They would like to include aerial hyperspectral imaging data with it, which would give a finer grid than the probe holes that we can do, but combining that with the depth information from the Subterra may be the most wonderful thing to do, right? But that's part of the outlook for that project, right?
About the software, do you have the software in the package, or it has to be brought by separately?
Our intention is, and certainly for the researchers, we provide our the operating software for the instrument. Then there's the analysis software, which so far for the research project, we've done that offline after the fact, okay? Because, well, we're figuring out how to do it, how to make it work. What the data I showed you are just preliminary. We're still developing that, okay? At the time it is sold to a journeyman user, an agriculturalist, for example, because they need to measure that kind of information, we would provide the analysis software would be included in the package so that you insert the probe into the ground and it would immediately show you the soil organic carbon estimate as a function of depth as a result of that. And then at the end of the day, when you may have done a grid or a sampling pattern, random stratified sampling, however you're going to sample your field, your farm, could show you a map like the one that I showed you, but that still has to be built in, but would be provided with the commercial sales, right?
Okay. And the next question you mentioned about the researcher who needs to calibrate by themselves. And like, would you help them as well with this one? Because of course it will be a new thing for us. So calibration would be ideal. Yeah.
Yes, we're certainly glad to help researchers with all of the insight. We have our Linda Barrett is our soil scientist who actually does that machine learning models. It's done in the Python environment, and we're happy to share with researchers how we do that, because it's all about doing it better and doing it in a way that's applicable to diverse ecosystems, right? The Boku group has their own expertise that they have chosen to go along their own path for the analysis rather than following what we are doing, which gives diversity. They can do that. But we're also willing to help people along the path that we have chosen for the analysis that I described, right?
And the last question from my side. Can I get a published article where I can see that in how they used it? Like, do you have do you have any paper? Like, do you have any researcher who bought it or who rented it and got a result and got a published paper out of it?
Well, the research with the Subterra Green hasn't been published. We do have a published paper on archaeology from some years ago, but that's not soil organic carbon, right? We do have conference presentations that we've presented on different stages of this project. We do intend to publish it in the future. The Boku people have their project is underway. It's maybe a year or two behind what I described what we're doing, because they started a little later. And they will publish the data as well. But all of that is in progress, right?
Thank you so much. That's all.
If I may jump in real quick, sorry about that. We do have our USDA SBIR Phase 2 report that is in the works right now. That is something that correct me if I'm wrong, David, but that we do intend on publishing down the line a little bit after some refinement. That is something that we'd be happy to pass along, though, when that's ready. I think we aim to have that completed within the next couple months or so, certainly by the end of the new year. Sorry, by the end of this year.
Yes, that'll have a lot of documentation and organized, because it's reporting to the federal agency that supported the work, right?
Great presentation. I had two small questions. So via your research, is it possible to identify hard water or salinity as well? And second question is whether this also gives an estimate of the water table in a specific area. Thank you.
We haven't tried to measure the water table. In the current data set, we do measure water content in the soil, okay? We've been focusing on the soil organic carbon so far, but our ultimate analyses will have three-dimensional maps of the water content. And that could presumably be examined for evidence of a water table, right? In most circumstances, the water table is below the level of the probe because of the nature of the agricultural land that we're in. But there may be circumstances where we would identify that, right? The spectra do contain two large peaks of water. The free water and the surface absorbed water have slightly different spectra. But that, as I say, that refining those data is still ahead of us, right? The other point that you mentioned is soil salinity is hugely important. In the United States, the whole western half of the country, where in fact a great deal of the high-value agriculture is located in the United States, the land is irrigated. The Colorado Basin, which is the large central basin in the mountainous area of the west of the United States, is running short on water. Irrigation water is in short supply, and farmers will not be able to get the amount of water that they're accustomed to, because it just doesn't exist. The river flows because of climate change has declined. So the limiting thing of agricultural production is salinity in the soil, because that determines how much irrigation water you need to use to keep the soil productive, right? And so that is on our plate to do that. We would like to engage in a project to measure soil salinity. Soil salinity does change the spectroscopic properties of the soil. So I think it's something that we would measure, but it needs a research project, and one that we'd very much like to engage in. As a private company, we do need funding. We can't do things on our own nickel, right? Because nobody pays the bills, right?
Then I will barge in again with more questions. What about very organic soils? Have you experience with that?
Some of the work that we did in phase 1 was at the Bath Nature Preserve. And this is some of the areas were not farmed. It was a nature preserve area. We even had one area that was a forested area, which generally has a much higher level of organic content in the soil, reaching quite high levels, right? And that works fine. It just needs to be calibrated in the same way that we have done, and we've been able to map those, right?
And when you say they're quite high, what are we talking? Above 12, 15, 20% carbon in some soil layers? I mean, often in forest, you might have the horizon in the very top, which is almost completely organic.
Almost all organic matter, which would come to something like 25 or 30% carbon, just because the organic matter has other things in it, right? Hydrogen, oxygen, nitrogen, things like that. And yes, we have been able to map areas like that. We haven't done swamps per se, which would be really the highest organic matter, but we've done wetish land, including forest land. And the mapping in those areas worked fine, right?
A question. So is it possible to visualize that a farmer who's interested in organic farming, who uses organic, composting, mulching, etc. Your technology can identify what's the best way to increase the carbon in the soil. Is that a right assumption?
Yes, that's one of the applications. That would be a very important application, yes, because land is more productive if it has more organic matter in it, and our organic farmers, of course, obviously would like to go in that direction.
Got it. So essentially, for a farmer, if he has plans of using 3 or 4 ways where he feels he can improve the organic carbon, your technology can tell him which is the best way to improve the soil carbon. So
that's right. And if you have a very good process, if you're more on the commercial farming side and you do something like no-till or cover crops of different types, if you do a very good process, you might be able to improve the soil organic carbon by 1% of its original organic carbon content in a year, right?
Wow.
So that's the kind of precision that we're aiming for in doing these measurements, okay? There are studies in the United States, particularly at the Ohio State University, the agriculture, it's what we call land grant university in the United States. And they have investigated in studies over a few decades of trying to improve soil organic carbon. This is before our instrumentation, okay? And over that period of time, you can see systematic trends as a result of certain agricultural methods, as I mentioned, no-till, cover crops, things like that, right? But there's a lot of noise in it. If you're going to have a program for improving your land, you want to see a change in a year or two. If you have to wait 5 or 10 years to see a change that you can measure, that's never in terms of a business model. You're going to go broke, right? So that's our role, what we're trying to do, right?
Yeah, super. I just had a question regarding the forest ecosystems and the more remote ecosystems. And Is it with in terms of mapping, does the GPS and systems like that still manage to get satellite data, or is it quite patchy because of how remote they are and how much tree cover and things like that interfere?
Remoteness is okay. The satellites have worldwide coverage for GPS. We haven't noticed a problem in the forest we're using, although it is, if it was very heavy forest cover, jungle or something, right? Rainforest, then there might be a problem. But in the temperate forest that we've investigated in Ohio, we're able to track it already. What one notices that the precision, GPS normally gives you the precision, the uncertainty of your location measurements, which with the standard one we use on the instrument, it's a 0.5 meter to a meter, that kind of distance, right? And those uncertainties can become larger if conditions are not ideal, right?
Yeah.
Super. Hi again. So there are lots of various programs around the world focused on desert greening, which involves, using technologies like half moon or other areas for water harvesting and kind of claiming the desert back. So does your technology also help in identifying the regions or areas where the maximum impact of such schemes can be implemented? Because if if there's a soil which is still organic matter, maybe that's a better candidate for reforestation exercise than something which is close to no organic matter.
We don't have experience in that kind of desert territory. But it would be up to the researchers, the principals concerned, to design the project. One could do the measurements, and if organic carbon measurements were to help in that project, it would help. But we don't have the direct knowledge of those kinds of projects.
Yeah, I think we've managed to go through all the questions, and there's a lot of good questions there. And of course, if there pops up any more questions, then I'm sure you're welcome to get in contact with both Russell and David. But I think for now we can end here and say thank you very much to both of you for coming today and speaking to us about your product. It's been a really interesting discussion.